So let us continue with our discussion about algebraic structures that we are doing this semester using this free textbook, uh, Abstract Algebra Theory and Applications by Judson. So far, actually, we have talked only about one algebraic structure, that is a group, and we talked about various groups. Now, today is going to be the kind of last formal uh, lecture or presentation for this particular course, and all the other material will be posted in the script form. Okay, so what we will do today is that we shall just extend our discussion to some other algebraic structures, and there are many, and we shall consider a few more. So we discussed groups. Now we are going to talk about another algebraic structure, which is called a ring. Okay, it's groups, and now our next topic is that of rings. So how do we define a ring? Not very much differently. We are just, as I said, we are going to be building upon or building up on our structure that we had studied and discussed, that is groups. So here, say we have a non-empty set R, which is an abelian group or a commutative group with respect to an operation. Let's call that operation addition. And then we also have another binary operation in there, that is multiplication, which is associative, and in addition, that satisfies this property, that is A cross B plus C equals A cross B plus A cross C for all A, B in R. And actually, in English, we will say that this means the multiplication is distributive over addition. Actually, this will sound better if I simply say it like this, that this is distributive over addition. Okay, so let's take up some examples, and we will again be, let's just build the, mostly build upon the examples that we already know. So for example, we may take this, sorry, if you look at the group of integers, okay, with plus and addition of integers and multiplication of integers as binary operations, then this is a ring. We all know that the multiplication of numbers is associative, and the multiplication of numbers that distributes over the addition. And going in the same flow, we have say another ring. Say for instance, we talk about, say we take the integers modulo, say 6. I could have taken any number, but I just chose to take modulo 6. Okay, so in here also all the properties are satisfied. That is uh, the integers modulo 6, they are an abelian group with respect to addition, and this multiplication modulo 6 is a binary operation. In this, it is associative, and you can easily check that it distributes over the addition modulo 6. Okay, and we can continue with these examples, and say for instance, we may take the, say we call E to be the set of even integers. Okay, then we have seen that that E is also a group with respect to addition, an abelian group, and at the same time product of two even integers is even. Okay, and this is a general property, doesn't have to do with even or odd. That is multiplication of number distributes over the addition. So this is also a ring, and of course a slight difference between this ring and this ring is this, that it does not have any multiplicative identity. Okay, and identity actually. All right, and I could do this. Let me just do this here so that these are well aligned, and we may take another example. Let's just go to, for instance, an example that we had taken in the beginning for say groups. Say we take M2R, okay, to be the additive group of all the 2 by 2 matrices with real number entries. Okay, so 2, 2. Okay, and we are keeping things simple in this case. So we have A, B, C, D. All right, where A, B, C, D, they belong to what? They belong to the set of real numbers. Okay, let me just reuse informal. Okay, they're all reals, and so M2R, this is a ring with okay, is a ring in is a ring with addition and multiplication of matrices. Okay, and you may notice this, don't have to notice, you already know this, that this addition is the operation plus, which will make it an abelian group, and multiplication is the multiplication of matrices, which distributes over addition, but it's non-commutative. Okay, all right, and going in the same style. Let's talk about another very famous ring, say, or we will talk about it a little later. I meant the polynomial rings since I just mentioned it. Okay, so in case I don't get time to talk about this in this particular presentation, we will have it posted. Okay, so I'm just putting it, dot, dot, dot here just to keep in mind that we have to discuss about it. And here is another interesting uh, ring. Okay, and let's just call it the Ring of Quaternions. Okay, all right. I mean, you saw quaternions. We consider the quaternions as a group with 8 elements. Okay, but here we are going to do it in a very different way. We are going to take that, or we are going to use, those elements plus minus 1 plus minus I plus minus j and plus minus k in a different style. Okay, that is, we are going to take that as a plus bi plus cj plus dk, so that a, b, c, d, they all are, say, real numbers. So that is the sum of two elements that are like this, would be, just as I said, added component wise. And for the multiplication, we will just go by the same general rule, that is our I, j, k, they would be, they will all satisfy, sorry, I cross I is, remember the same thing is j cross j, okay, and equals k cross k, and each one of them is how much? -1. Okay, and remember Hamilton developed this for the multiplication in 4 dimensions, and these just become anti-commutative. Okay, I and j cross k is negative k cross I. All right, and actually we may I'll just write it down, and negative k cross j I meant. All right, and then we have k cross I, k cross I equals negative I cross k, and just to show that that's anti-commutative, and we know we took I cross j as k, okay, and j cross k as I, and then k cross I as j, okay, all right. So applying this to this product, we can just distribute, and you know, just using the property that this type of multiplication distributes over addition. Okay, what we are not proving that here formally. We can just go ahead and distribute it over. So, what we have is this will simply become what? A1, A2, sorry, this is just too light. Okay, then no, not this one. I mean, there's nothing wrong in taking it that way, but let's just distribute according to the way I had in mind. So this is A1, B2I, and then what we have is A1, C2, J, okay, and then likewise going here, this will give us A1, D2K. So, these just went over as usual, and I'm not going to like make you listen through all of these guys. So then you got B1, A2, and it doesn't really matter which way you take it. I, right? And then next you got B1, B2, and then you will have I cross I, that will make it negative B1, B2, right? And then we will have B1, C2, and what it gives is I cross J. So that will become B1, C2K, and then we have, say, B1, D2, and that's I cross K, so that will become negative J. So we can continue in that style, and our product will become, so collecting all the terms, and combining the constant term or the non-ijk term, all right, and the coefficients of ij and k, we shall find that the product equals this. So this of course is a non-commutative ring, and it also has an identity. And what I just noticed is this, that I'm just repeating the stuff in the book for you. So anyway, so here, there are some additional properties that if we have a non-zero, we have an identity, as I said, and every non-zero element will have a multiplicative inverse, okay? And then the multiplication and addition, all those properties, they interact with, sorry, all those operations, they interact with these properties. And again, as we did for a subgroup of a group, we can come up with like fewer criteria for a structure to be subring of a given ring. All right. So this is how, a ring is formulated. And then subring, I'm not, in this particular presentation, I'm not covering it. We will have some scripted discussion about it, all right, a little later. So what we just did was that, that non-empty set endowed with two binary operations, both associative, okay, can be a ring, and a ring can be commutative or non-commutative, right? It depends on the commutativity property, depends on this part here, the multiplication, because with respect to addition, it already has to have, it does have to be abelian, or that has to be commutative, may have an rather a multiplicative identity, okay, or identity, or may not, okay, and in general, there is another thing. For instance, if you look at the ring of integers the way we took, that is z plus and then product, what we have is that if we have a times b equals 0, then that automatically means that one of them has to be 0, right? That either A is 0 or B is 0, right? But if you looked at this, say for instance, you look at the another ring that we had, say Z6 with addition modulo 6 and multiplication modulo 6, there you could see that if you took say 2 times, okay, and in modular multiplication I'm taking this as 3, so that will be 6, that will be 0 modulo 6, but neither of these is a 0, right? So what we say here is that there may be some rings that have 0 divisors, that is, product of two non-zero elements may turn out to be 0, okay? So what we are going to do now is that we shall start, refining our structures and build up newer structures, okay? So now let us do this, that is, look at the rings that are commutative, that do have multiplicative identity, and that do not have any 0 divisors. So let's give them a new name, and we are going to call them, actually I'm not giving them a new name, this name has already been given much before even I was born. I was even born, I meant. So integral domain. So what is an integral domain? Commutative means multiplication is commutative. So a commutative ring, let me call that I, okay, with multiplicative, sorry, multiplicative identity, okay, is an integral domain, or let's write it slightly different, with multiplicating identity and with no 0 divisors is called and an integral domain. All right. Okay. So in other words, if I just write it, say symbolically, to avoid writing too much English or too much any language, not just English, sorry, uh, times, okay, all right. So here, commutative, commutative ring, this with multiplicative identity, multiplicative identity is called an integral domain if if for any two elements A and B of this this commutative ring, if any product of any two elements is zero, then that will have to imply that at least one of them has to be zero. Okay, and so this will be called then integral domain. And an integral domain, remember this, we have an identity, but we may not have a multiplicative inverse. But still in an integral domain, okay, in an integral domain, okay, say we got this. So even though we do not have the multiplicative inverse for any non-zero A, okay, all right, A cross B equals A cross C, or A multiplied by B equals A multiplied by C, always implies that B is C. That is, A left cancels, and that holds for every non-zero A and all the other B and C in I. All right, I'm not writing it. I can write it, but let me just, just look at this recorded narration as a recorded script, and that is true simply because you can look at this. That is, if I have A cross B equals A cross C, then I can add negative A cross C to both the sides, right? And then on the right hand side we get 0. Here we are using the inverse property. And now when we are factoring out, notice this here, that I know you have done all that for all practical purposes since grade school, but formally what I'm doing is that I'm just reversing the distributive law, right? So we got this here, right? Now, since A is not equal to 0, right? Then in order to be an integral domain, we must have the other factor equal to 0, which happens to be B minus C, right? And then adding C on both the sides, or adding the inverse of negative C on both the sides, gives us B equals C. The book does a good job of proving other way around also, and many other properties like this. Okay, so what we did was we just saw two more structures, other than group. One is ring, the other one is integral domain. So if you look at this, then this is also an integral domain, right? Z is an integral domain. Z modulo 6 is not an integral domain, right? Okay. And if we look at the even integers, it doesn't have any multiplicative identity. So this is not an integral domain by this criteria. Okay. Now here again, you can see this here, multiplication is not commutative. So it is not an integral domain. Okay, we have multiple multiplicative identity though, and so this is non-commutative, and we have seen many times, and you can see it again, that has zero divisors. Okay, so why don't we just construct a zero divisor quickly? So let's take a 2 by 2 matrix. Okay, all right, so 1, and I'm taking -1 here, 1, -1. This is the non-zero matrix, and I know, or we know, that they multiply by row by column. So if I remove this negative sign, this one, hopefully they should multiply to 0, and yes, so it has 0 divisors. So it's not an integral domain, right? And let's see. And then here, Ring of Quaternions is not an integral domain either. Why? Because they are not commutative. Okay, so we saw that we have some integral domains and some not. So let's just take a couple of integral domains from here. One of them is simply z plus and the product now. And remember this, that if we look at this z6, because we just saw that, right? I'm just repeating myself here. Then this is not an integral domain, but if you recall our previous discussions, then okay, this is not an integral domain. But if you have this instead of say 6, say you had something like say 5 here, then you saw that that's a prime number and could not be factored, and this did not have, okay, this does not have zero divisors, right? Okay, so you saw that this is an integral domain, right? And in fact, if I take the integers modulo prime, any prime p, okay, all right, so p is a prime integer, okay, is prime. Let's take positive integer, okay, integer, then this is an integral domain. All right, now let's just go towards one more structure for this session, one more structure. All right, and then we will just talk about the relationship amongst them. Okay, so now let's look at this here, the difference between this integral domain and this integral domain. Okay, so in here, if I look at this, then non-zero, or rather, let me just plus minus 1 are the only non-zero elements that have multiplicative inverse. Okay, So what that means is this, that if I do this, that is, if I took the non-zero integers, okay, and look at them with respect to multiplication, they cannot form a group even though they have an identity. Okay, so it's not a group. However, if we look at this one here, then in here, remember, actually there was a name for this Z5 star that we gave, okay, and that was we called it U5, right? That is the integers modulo 5 that are units, so that have multiplicative inverse, and they will be all of just 1, 2, 3, 4. Okay, so this is a group, right? So what happens is this, and while here this with respect to multiplication is not a group, okay, and this one is an integral domain in which the non-zero elements do form a group. So let's go ahead and just take up one more structure or algebraic structure, okay, that is, if we have an integral domain, if this is an integral domain such that the non-zero elements, okay, such that the non-zero elements here, okay, they form a group. Okay, oh, I'm so sorry, what did I do? One moment. Yeah, here. That is, they form a group. Then we say that this is the field. Okay, is a field. Or on its own, you may say that, you know, this is a field, okay, with, okay, field if there are three conditions. One of them is, and of course, by F star, what we meant is, by F star, we meant F with the additive identity removed. Okay. All right. If so, if this is an abelian group, all right, and I'm writing it very casually, so make sure that you compare it with the book or other resources. Okay, so then the non-zero elements, okay, by star I mean the non-zero elements, okay, with respect to multiplication is an abelian group, so of course it does have a multiplicative identity. I don't have to say that, right? And it will not have any zero divisors, so it automatically is integral domain and then a field, and then the last condition being the distributive property, right? So A cross B plus A cross C. So we just saw that you know, all the integers modulo positive prime, they form a field, okay, with respect to the addition modulo P and multiplication modulo P. And a reason I just brought this statement up again, is this, that the book very nicely proves for you that is a field for all positive primes. Okay, so primes P, that is any finite integral domain is a field. Okay, integral domain is a field, and of course this is not the case for infinite integral domains. For example, we saw that if we took z plus and then the multiplication, that is not a field. Okay, however, remember we had seen the rationals, okay, that we form by taking equivalence clauses in z cross z. Okay, so that is a field because non-zero rationals do have multiplicative inverse. So that is a field. Then the reals is, they also form a field, and there is a lot that it takes to extend this field of rationals to this field of reals. Okay, so we can take that up later. So that's another field. Okay, and we will have some more examples in a few minutes. But before I go ahead, excuse me, let me just bring for you the ring of polynomials. Okay, and ring of polynomials simply is, let me describe the writing and then bring it back to you. Okay, so here we are taking our commutative ring with identity. I just brought the definition over from your book. And if you consider, expressions like these, and here the leading coefficient is not equal to 0 because that gives us the degree. We call x an indeterminate, all right? And if we consider the set of all such polynomials where these coefficients, okay, they are in the ring R, we call that the set of polynomials with the coefficient in R. And if we just use the addition and multiplication, okay, and use the distributive property in a routine manner, we can see that this is a commutative ring. Okay, and with identity, because one of course is a polynomial. Why is it a polynomial? It's a polynomial of degree 0, right? Isn't it? Because there is no other term there. It has only constant term, and that is a 1. So for example, 3 minus 2x squared plus 7x to the 5 plus x9, that's that's an element of the polynomial. Sorry, that's a polynomial in the ring of, over the ring of integers. Okay, or if I took say pi x cube, say minus 6, that's a polynomial over, on this ring where R is the set of real numbers. Or if we want, we can even take a polynomial over rings like, Z6. And just for a little, like, I would say excursion, all right, let's just see. You know how to add them, you know how to multiply them. So let's take an example in Z6x, how two polynomials will add or multiply. So for example, let's take these two elements in Z6x. So if we add them, okay, so 4x cube plus 2x plus 2x cube plus 3. So adding them means we are adding these two together, the x cubes. So that will be 6. 6 modulo 6 is 0. So that will become 0x cube. Now 2x is just by itself. There is no other x. So we will have 2x and there is only one constant. So in this ring of polynomials, these two will add up to 2x plus 3. And say we are multiplying them together, okay? Or let's just go ahead and do the, what did we call it? The FOIL, right? First, okay? Then outer, right? Then inner, all right? And last, just remembering your algebra 1 or 2, wherever you did it. So what do we get? 4 times 2 is 8, modulo 6 would be 2, and x cube will become x to the 6. That's the first. And for the uh, outer, we have 4 times 3 is 12. 12x cube is 0, so I'm not writing it. Okay. And then we have 2 times 2 is 4, so then we get plus 4x cubed. All right. And then we go to the last, and last is 2 times 3, that is 6x, and 6 is 0. So these two multiply to how much? 2x cubed, 2x to the 6 plus 4x cubed. We did it just for having an excursion, and then going further. So here is just another, important property that resembles what we did before that I wanted to bring up. And this is from page 302 of our textbook by Judson. Okay, so if I have fx and gx, two polynomials where gx is non-zero, then what we will get is we will get a unique quotient and a unique remainder. Sorry about that. Okay, a unique quotient, Q for quotient, and unique remainder. And here they will be related in terms of degrees. All right, that is degree of the remainder will be less than the degree of the divisor. So as an example, let's take up. And also do not forget that here we are talking about a field, polynomials over a field, okay? So let's quickly apply the division algorithm on this one. I mean, this is going to be simply an algebra 2 example that you had done, okay? All right, wherever you did it. So here we got pi x to the power 4, then pi plus 1 x square plus x plus 4, and here we have x square plus 1. So what do we do? Compare these two, so we get pi x square. Then we will multiply these two quantities, so get pi x to the power 4 plus pi x square. Then do the subtraction. So what will happen? This pi and this pi will cancel. They will cancel anyways. So what steps down for you? X square from here plus x plus 4, right? Now this is x square, and now when we compare this x square, this x square with this x square, all we need is a 1. So we multiply the divisor by 1, we simply get this. Okay, then do the subtraction. So as desired, our remainder is how much? The Rx turns out to be x plus 3, and this is our quotient. So this again is just just the algorithm that we did with the integers before, and we can do it, say, again, just for a little demonstration for a non-traditional field. For instance, let's take something into as simple as in Z3. Okay, so we will consider a polynomial in Z3 over Z3. Okay, so here we have Z3, the field with the elements 0, 1, 2, and what we are doing is we are dividing 2x to the 4 plus x squared plus 2 by x squared plus 1. So comparing these, we get x squared. So what we shall actually 2x squared. So we have 2x to the 4, then plus 2x squared here. So what we are going to get is, well, of course, these two will cancel. And here, when we take this x squared minus 2x squared, who is the inverse of 2? That's simply a 1, right? So this will become how much then? X squared plus x squared, because again, additive inverse of 2 is 1, right? So again, on the bottom, we get 2x squared plus 2, right? Okay, and now what will happen is plus, so in order to obtain that, we have plus 2 here, multiply by 2, we get 2x squared plus 2, and here the remainder turns out to be 0. All right, okay, so what we find is this then, that this quantity fx is 2x squared plus 2 times how much? X squared plus 1. And let's just quickly FOIL it and see if that is correct, because the remainder turned out to be 0. So we have 2x squared, so 2x to the 4, right? And then plus 2x squared, then again plus 2x squared from the inners, right? Then a 2 from the last, right? So we have 2x squared. These two together become 4x squared, which will become 1. And then we have plus 2. So here our quotient is how much? 2x squared plus 2, remainder is 0, or in other words, this is a factor of this polynomial, as polynomials in Z3x. All right. So now let me just conclude this presentation by one last remark. So let's say we have a field F, all right, and we have this, that is E is an extension of this field, that is E is also a field, okay, that contains F, and of course there will be two operations. So these operations for F are the same operations, and they're just restricted to F, okay. So in this case, as it appears, E contains F, we may call E an extension field of F, okay. And we have what is called fundamental theorem of the field, fundamental theorem of fields, and I'm just writing it very, very informally, that say F is a field. Okay, all right, and Fx is a polynomial in over this field, and Fx is not a constant, or let's say the degree is greater than or equal to 1. Okay, so we can always, we can get an extension field, okay, of F. So actually extension field E of F such that F has a 0 in E. Okay, so I shall post some scripts showing you some interesting applications of this fundamental theorem. But let me just you know conclude the video part of this series with this one here. So hope you found them of some use, and let me know if you have any questions. All right, thank you very much.